Hello everyone, I'm Ayush Vishwakarma. Today I'm going to be presenting the CI activity of control systems, which is based on a open loop and feedback control system, which we have simulated for the responses of and to evaluate improvements in system stability, damping overheat, and setting time due to state feedback. So this CI activity is going to be presented by me, that is Ayush Vishwakarma, Siddhi Vaksaure, Pooja Ishtaki, and Sarthak Kamble. So let us move directly onto the simulation. So basically, this is the simulation. The purpose of this model is basically in control systems, the performance of system is evaluated based on parameters like stability, damping overshoot, and setting time. An open loop system operates without considering the output, meaning it can correct errors automatically. As a result, it is generally less stable and more sensitive to disturbances. To overcome these limitations, we can use a closed loop feedback control systems where the output is fed back into the system to improve performance. This project we specifically use state feedback control where all the system state variables are used to design the controller. The system is modeled using the state space representation given by the state equation, that is x, ax plus bu, y, that is output equation, cx plus du. This is for the both open loop and the closed loop system. So in this simulation, the top model represents the feedback control system, that is basically the closed loop system, where the gain matrix K where the gain matrix K is going to be adjusting the system behavior. The bottom model hereafter represents the system without feedback control or simplified version of the for the comparison. So by applying the step input, we observe that system responds in both cases. The results are displayed using scopes, allowing us to compare the performances. The main objective of the simulation is to demonstrate how state feedback improves system stability, reduces overshoot, and decrease setting time compared to the open loop system. So here the closed loop system and the open loop system both are going to be compared by running the simulation. So this is all about the introduction. Let us move forward. I request Siddhi to continue with the further.
Hello, I'm Siddhi. Today I'm presenting my Simulink model on full state feedback control system. In this model, a step input is given as reference multiplied by KR, that is 45. The system uses state space representation where the output state X, that is here, then feedback through the gain matrix, that is 457, that is here. This feedback k of x is subtracted from the reference input to form a control law u is equals to kr minus kx1, which improves the system stability and performance. The process signal is applied to the state space block defined by the matrix A, B, C, D, and the output is observed on the scope here. Uh, then a second section below one with full state controller block is also included for the comparison. This model demonstrate how state feedback helps in achieving better control, faster response, and improve accuracy in practical systems like robotics, industrial automation, and many more. Thank you.
I'm Pooja Ishtake. This diagram shows a full state feedback control system implemented in Simulink. First, the step input is provided to the reference signal to the system. Then this input is passed through gain KR, which scales the input. This helps the system reach the desired output properly. Next, the signal goes to the add block where the system subtracts the feedback signal from the input. So basically, it calculates the error. The state space block represents the actual system using mathematical equations. It generates the output states denoted as X. Here is the X. So the states are then sent to the matrix multiply block where they are multiplied by gain matrix K. This produces the feedback signal Kx. This feedback is sent back to the subtracted at the back, and then this is subtracted at the add block, which helps in correcting the system response. The scope is used to visualize the output response of the system. In this lower diagram, instead of connecting everything manually, a full state controller block is used. It performs the same operation internally, combining input scaling and state feedback automatically. Finally, both the outputs are shown on the scopes to compare and verify that both methods give the same result.
In this project, we modeled and simulate both open loop, and full state feedback control system using MATLAB Simulink to analyze their performance in terms of stability, damping, overshoot, and settling time. In open loop configuration, the input is directly applied to the state space model without any feedback, which results in the response that shows high overshoot, noticeable oscillations, and longer settling time, indicating that the system is under damped and less stable. To improve this behavior, we implemented the state feedback control system using the control law U is equal to KR minus KX, where K is the gate matrix and X represents the state vector. By introducing this feedback, the system continuously corrects the output based on the current state, leading to a significant improvement in performance. Let's run this program. Um, from the simulation results, it is clearly observed that the feedback control response has reduced overshoot, faster settling time, and a much smoother curve with minimal oscillations, which indicates that better damping and enhanced stability. The comparison between both systems shows that while the open loop system lacks control and exhibition for dynamic performance, the state feedback system effectively modifies the system dynamics and shifts the poles to achieve a stable and well damped response. Hence, this project demonstrates that the state feedback control is a powerful technique for improving system stability, reducing oscillations, and achieving faster and more accurate response in control system. This was all about our project.
Thank you so much. Very well, Naman. I